Hello everyone, welcome to new class. Today's class is about string efficiency. So before going through the string efficiency, let us discuss about the potential distribution over suspension insulator string. So we know that a string of suspension insulators consists of a number of porcelain discs connected in series through metallic links. So here there are three disc string of suspension insulators, and the porcelain portion of each disc is in between two metal links. So this is porcelain portion and these are the metallic links. So each disc forms a capacitor C like this. So each disc forms a capacitor C, and this is known as mutual capacitance or self capacitance. So C is mutual or self capacitance. And if there were mutual capacitance alone, then charging current would have been the same through all the disk, and consequently the voltage across each unit would have been the same, say V by 3. So if the capacitance is same, then current through, and if there is only mutual capacitance and if the capacitance are same, then the voltage across each capacitance will be equal. That is, here there are three capacitances, so let us say that it is V by 3. But in actual practice, the capacitance also exists between the metal fitting of each disc and tower or earth, and this is known as shunt capacitance C1. So C1 is known as shunt capacitance. So there exists a capacitance between the metal fitting of each disc and tower. So due to the shunt capacitance, the charging current is not the same through all the disc of the string. Therefore, voltage across each disc will be different. That is, V1, V2, V3 are the voltage across each disc or capacitance. And the disc nearest to the line conductor. So, this is line conductor. So, we have discussed about the suspension insulators in the previous classes. So, this is line conductor and this is tower. So, the disc nearest to the line conductor will have the maximum voltage. So, here V3 will be greater than V2 and V1. So, here V3 will be greater than V2 or V1. So, while considering the potential distribution over a string of suspension insulators, the voltage impressed on a string of suspension insulators does not distribute itself uniformly like this across each disc due to the presence of the shunt capacitance, and the disc nearest to the conductor has the maximum voltage across it, and as we move towards the cross arm, so here there is cross arm, so as we move towards the cross arm, the voltage across each disc goes on decreasing. Now let us define the string efficiency. So the ratio of the voltage across the whole string to the product of number of discs and the voltage across the disc nearest to the conductor is known as the string efficiency. That is, string efficiency is equal to voltage across the string divided by n into, n is the number of discs in the string, into voltage across the disc nearest to the conductor. That is, we can write V divided by N into V3, or percentage string efficiency. Percentage string efficiency is equal to V divided by N into V3 into 100. So, this is the string efficiency. And the string efficiency is an important consideration since it decides the potential distribution along the string. The greater the string efficiency, the more uniform is the voltage distribution. Now let us derive the expression for this string efficiency. That is, string efficiency is equal to voltage across the string divided by product of number of discs into voltage across the disc nearest to the capacitor. So let C be the self or mutual capacitance and C1 be the shunt capacitance. Assume that the shunt capacitance C1 is some fraction of the self capacitance. That is, let C1 is equal to K into C. So, starting from the cross arm or the tower, the voltage across each unit is V1, V2 and V3. Now, consider the nodes A, B and C. Applying Kirchhoff's current law to node A, that is KCL at node A, then we will get, so here I1, I2 and I3 are the currents through the self capacitance, then small I1, I2, I3 are the currents through the shunt capacitance. So we will get I2 is equal to I1 plus capital I1. Then what is I2 in terms of V2 and C? So we know that the current through the capacitor, that is current through capacitor, is equal to V divided by XC. And what is XC? XC is equal to 1 divided by omega C. And we get V omega C as the current through the capacitance or capacitor. So, applying that here, what is I2? So, I2 will be equal to V into, V is V2. So, the voltage across the capacitor C, that is here it is V2. So, V2 into omega into capacitance is C equal to I1. What is I1? So, here what will be the voltage across this capacitance? That is voltage across the shunt capacitance C1 here. So, the voltage across this capacitance will be V1 because it is this voltage. So, it is same as the voltage across that self capacitance. So, it will be V1 into omega into C1 plus then I1. I1 is this current and that is equal to V1 into omega into C. So, that is at node A. Now, we can rearrange this one. That is, put the value of C1 as K into C. So, we will get V1 omega K C plus V1 omega C. and that is equal to, here we will get V1 omega C into 1 plus K. That is V2 omega C is equal to this one. So from here we get V2 is equal to V1 into 1 plus K. So this is first equation. Now applying KCL at node B. That is KCL at node B. Then we will get I3. That is I3 is equal to I2 plus capital I2. So what is I3? I3 is that V3 into omega into C. So here what is I2? So here this is I2 and this I2 is equal to the voltage across this point and this point. So it is the sum of V1 and V2. So I2 is equal to V1 plus V2 into, so here voltage across this capacitance C1 is the sum of V1 and V2. So V1 plus V2 into omega into C1 plus I2 is the voltage across, that is V2. V2 into omega into C. Now put the value of C1 here, that is V1 plus V2 into omega into C1 is K into C plus V2 omega C. Now here omega C is common, so it is cancelled. So here we will get V3 is equal to V1 plus V2 into K plus V2. Now here rearranging we will get here K into V1, that is K V1 plus K V2 plus V2. That is, here we get V2 as V1 into 1 plus K, and we have to put the value of V2 here. That is, we have to get the values in V1 only. So here we will get K into V1 plus here V2 into K plus 1, and that is equal to K V1 plus V2 is V1 into 1 plus K. So V1 into 1 plus K into 1 plus K. So here we will get 1 plus K the whole square. That is K V1 plus V1 into 1 plus K whole square is 1 plus 2K plus K square. That is V3 is equal to, here after rearranging we will get here K into V1, here 2K into V1. So that is 3K V1. That is V1 into 1 plus 3K plus K square. That is V3 is equal to V1 into 1 plus 3K plus K square. So this is the second equation. So here V3 is the voltage across the disc nearest to the conductor. Now we have to find the value of this voltage across the string, that is the total voltage. So voltage between the conductor and the tower or earth. Is V. V is equal to V1 plus V2 plus V3. And here V1 is V1 plus V2 is V1 into 1 plus K. Then V3 is V1 into 1 plus 3K plus K square. So here after rearranging we will get V1 into 3 plus 4K plus K square, or we can write V is equal to V1 into 1 plus K into 3 plus K. So this is the voltage across the string, and V3 is the voltage across the disc nearest to the conductor. This be the equation number 3. So from the first equation we can write V1 is equal to V2 divided by 1 plus K, and also from the second equation V1 is equal to V3 divided by 1 plus 3K plus K square, and also from this equation we can write V1 is equal to V divided by 1 plus K into 3 plus K. So this is the relationship between the voltages across each disc and the total voltage. It is voltage across the string. So from this we can write V1 is equal to V divided by 1 plus K into 3 plus K, where V1 is the voltage across the top unit. Also V2 is equal to V1 into 1 plus K, and V3 is equal to V1 into 1 plus 3K plus K square. Now the percentage string efficiency. So in this case, what is the percentage string efficiency? So it is the voltage across the string, that is the total voltage divided by number of discs. So here the number of discs is 3 into the voltage across the disc nearest to the conductor, that is V3 into 100. So in this case, the percentage string efficiency is equal to V divided by 3 into V3 into 100. Next is methods of improving string efficiency. So it has been seen that the potential distribution in a string of suspension insulators is not uniform, and the maximum voltage appears across the insulator nearest to the line conductor, and it decreases progressively as the cross arm is approached. And if the insulation of the highest stressed insulator, that is nearest to the conductor, breaks down or flashover take place, then the breakdown of other units will take place in succession, and this necessitates to equalize the potential across the various units of the string, that is to improve the string efficiency. So the various methods for this purpose are: first one, by using longer cross arms. We have the string efficiency is equal to V divided by N into V3, and this V3 depends upon the value of K, that is V3 is equal to V1 into 1 plus 3K plus K square in the case of 3 number of strings. So in this case also the V3 is depending upon the value of K, and K is equal to C1 divided by C, where C1 is the shunt capacitance and C is the self capacitance. So V3 depends upon the value of K. So the lesser the value of K, greater is the string efficiency. So lesser the value of K, V3 will be lesser, then string efficiency will be greater. So if the value of K is lesser, then V3 will be less, then we will get more string efficiency. So the value of K can be decreased by reducing the shunt capacitance. So in order to decrease the shunt capacitance, that is C1, so we have to decrease the value of C1. The distance from the tower must be increased, that is C is equal to epsilon 0 epsilon r into A by D. So capacitance is inversely proportional to the distance. So if the distance of the conductor from the tower is increased, then we can decrease the value of this shunt capacitance. So for that we have to use longer cross arms. But there are limitations of cost and strength of tower which do not allow the use of very long cross arms. So in practice, K equal to 0.1 is the limit that can be achieved by this method. So to improve the string efficiency, it depends upon the value of K. That is, we have to reduce the value of K, then only we will get greater efficiency. So to reduce the value of K, the shunt capacitance should be lesser. So to decrease the value of this shunt capacitance, so we have to increase the distance from the tower of the conductor. So for that we have to use longer cross arms. Then second one is by grading the insulators. So in this method, the insulators of different dimensions are so chosen that each has different capacitance. That is, the insulators are capacitance graded. That is, they are assembled in the string such a way that the top unit has the minimum capacitance increasing progressively as the bottom unit. So the capacitance value is increasing downwards. So the top capacitance is minimum capacitance. So at the top minimum capacitance value is chosen. That is, the capacitance is inversely proportional to the voltage. So this method tends to equalize the potential distribution across the units in the string. And this method has a disadvantage that a large number of different sized insulators are required because the capacitance values are different. So we need different values of or different sized insulators. The next method is by using a guard ring. Next is by using a guard ring. The potential across each unit in a string can be equalized using a guard ring, which is a metal ring electrically connected to the conductor and surrounding the bottom insulator. So the guard ring is a metal ring electrically connected to the conductor and surrounding the bottom insulator like this. So the guard ring introduces capacitance between the metal fittings and the line conductor, and hence it tends to cancel the shunt capacitance. And the guard ring is counted in such a way that the shunt capacitance currents I1, I2, etc. are equal to the metal fitting line capacitance currents I1 dash and I2 dash. And the result is that the same charging current, that is I, the same charging current I flows through each unit of the string. Consequently, there will be uniform potential distribution across the units because the currents through these capacitance are same. So, we will get uniform potential distribution across each units. So that is about the methods of improving the string efficiency. So while doing problems, we have to consider certain things, that the maximum voltage appears across the disk nearest to the conductor, that is the line conductor, and also the voltage across the string is equal to the phase voltage. So voltage across string is equal to the phase voltage. So voltage across the string is equal to the phase voltage. Phase voltage is the voltage between the line and the earth. So phase voltage is voltage between line and earth. So the voltage across the string is the phase voltage, and if we want to find the line voltage, then multiply with the root 3. So root 3 times voltage across the string gives the line voltage. So that is about the important points regarding string efficiency. So in the next class, let us discuss about the problems related to string efficiency. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.